Okay, so welcome everybody. I see a lot of people here, so that makes me very happy. Well, my name is Daniel, you see there, and I come from HLRS. HLRS is the High Performance Computing Center of the University of Stuttgart, and I'm going to talk to you about what problems in scalability we have in HPC. HPC is high performance computing. I don't know if there are many people that know about HPC and what kinds of machines we have. So I'm going to start talking about them, how they have evolved in time, what problems we are having with them, how we program them, and what ideas we have to solve these issues. And yeah. We are realizing that it's very important if you want to scale to solve all your data dependencies if you want your execution to be right. So, well, this morning we were already talking about how CPUs have evolved over time. In this graph we can see the evolution of the frequency of CPUs over time. So in the last recent years, we are not able to increase the frequency any longer. Intel planned like 10 years ago with the Pentium 4 to reach over 10 gigahertz. Well, I didn't see any 10 gigahertz machine around. And well, the problem is also that there are also no new ideas on how to speed up the CPUs by putting new hardware inside them. All the ideas, they were developed quite early, in the 60s and 70s. They were difficult to implement because they needed a lot of transistors. We developed technology. We were able to implement them inside the CPUs. And now there are no new ideas of how to make a CPU core faster. We can just make a larger cache, larger data structures inside, but that doesn't really make them a lot faster. So how do we try to make machines faster? We just add more and more cores. So in this graph, we can see the last 20 years of evolution of HPC. On the left column, we have the numbers of cores that the most performant HPC machine had. And on the right column, which is corresponds to the orange line, is how many teraflops per second that machine was able to deliver. So right now, the biggest machine has around 3 million cores and gives around, I think it was like 30 petaflops. A flop is a floating point operation. So yeah, I mean, this morning I saw discussions and people were talking about scaling to a few 10, hundreds. So we want to scale right now to 3 million threads at least. And we expect that we will just be increasing and increasing the numbers of cores. So we are talking about, I don't know, the number that we will get in the next years. And the problem is that, and we'll see it here, this graph is similar. I just replaced one of them, the number of cores, with how much performance is a core. And as you can see, it didn't change much. Even sometimes it goes down. It goes down because it's easier to build a machine with smaller cores and just put a lot more of them. But this is not usually good, and we will see a bit later why. So I'm going to talk about the machines we have at the HLRS. Right now we have a machine we bought in 2011, which has over 100,000 cores. And now we are going to get the new one, and when it's finished, it will have almost 200,000 cores. And this, of the new machine, the cores are IP-threaded cores, so if you want to get the maximum performance of them, probably you have to schedule 2 threads per core. That depends on the application and the amount of memory you have per core. So I don't know if you are familiar with Lambda law. It basically explains like if you have an application and your application has a part that is strictly sequential, you have no way of parallelizing it or run it concurrently with anything else of the program, and another part that you can parallelize, depending on what percentage of your application you can parallelize, what is the speed up you gain by adding more cores to it, by increasing the parallelization. So for example, here, if you have an application where 50% of your code is going to be just sequential, and the other 50% you can really parallelize, if you increase the number of cores to an infinite number, you will be still limited to speed up of like half of your time, execution time, because of this sequential part. Of course, if the parallelization is much higher that you can do, it will be better, but you will still get a part that you cannot parallelize and that you cannot go speed it up the application independently of the number of cores that you add. But the problem this has is that this is a very theoretical graph. What actually happens is something like this. And it's that there is some point where the more cores you add, the more threads you create, the slower your application becomes. And that's because in reality, you have to access memory, and you have to communicate and exchange data. So there is a moment where adding more threads just creates worse communication, much more overhead, and your application performs worse and worse over time. That's why we would really like to have one single huge core to program. Instead of... So, yeah?
One single socket or one core?
One single core. One single core that was able to deliver us 3 teraflops with a single thread. Then you will not need to parallelize anything. You just put the code that runs and no problems. But that's impossible to make. That's completely impossible to make. Otherwise, that is what we will be using right now. Yeah, and well, the problem you have this also is because most compilers, all they are trying to do is reduce when they use optimizations in your code, they try to reduce the complexity of the algorithm that you are using and to reduce the number of operations, but they almost never take into consideration what is going to be the cost of communication. They assume that the memory is there for free and that you can access it at any moment, and that it has 0 latency, but it's not like this. Yeah, and one of the problems also is that it gets worse over time because memory, we were not able to evolve memory at the same speed as the CPUs. They are able to deliver a lot more data, but the latency, that is like the time since you request the data till you start getting them, is still extremely high. Even if we are adding more and more cache, the problem with cache is that when you increase the size, to be able to have more data near the CPU, that's something you can do now with smaller technology, it also becomes slower. It also increases the latency. So now, inside any modern CPU, you can have even up to 5 levels of cache. Usually people know about L1, L2, L3.
L0, L4.
There is L0, which is usually the decoded already instructions, and L4 that you have in some Intel CPUs now, that is 64, 128 megabytes.
128.
Yeah. That's a bit, it doesn't have a lot more bandwidth than real RAM, but you can access it quite faster. That's the main advantage with RAM. So how do we program now HPC machines? We usually use C or C++ or Fortran, which is basically programming in assembler. These are just, it's basically assembler, as we saw in a presentation earlier this morning. It's just a basic translation from one to another. Inside the node, I forgot to say that when you have so many cores, you divide your HPC machines into nodes. Each node has maybe 1 or 2 CPUs. Each CPU has a lot of cores inside, and they usually share the memory, and at least the address space of the memory. So each thread can access all the memory within this node. And all the other, so you've set up a lot of nodes, and they are in an internal network. So if you want to communicate with inside a node, usually you use something like OpenMP, which basically is just normal threads. And if you want to communicate between different nodes, you use message passing interfaces. So that's how we are doing it till now. And we are not using, up to now, functional languages because they have some disadvantages for these machines. And maybe I will be a bit controversial now. So the problem is that they use too much memory. That's one of them. They're usually, when you measure it, they have a tendency to use to allocate much more memory, and you have no control over it. And memory is extremely important. Usually, there are some applications in HPC machines that where you reduce the number of cores you are using so that a thread can have more RAM. And usually, you have around 4 gigabytes of RAM per core in some cases. Another thing is that you have no control over the hardware where you're running with functional languages. Like you cannot optimize, for example, to fit your data structures into your cache of the CPU. You have no control of if it fits, it's not fits, how many cache misses you are having. So that's the problems that they have right now. And for us, it's extremely important performance. We consider extremely good if you are able to obtain a 2% faster performance. That can be a lot of money at the end of the day. Okay, so how applications are executed? Coming back to the topic of programming. So if we have this nice application, which has like let's say 4 tasks, we can run it sequentially, one after the other. But if we give the information about what are the dependencies between these tasks, and we have more cores, we could say like, well, things that where the dependencies have already been resolved, we could run it concurrently. Like in this case within the red and the orange part. So if you have a good scheduler and you know the dependencies, you can improve your execution. If you have even more information about when the data is accessed, you can further improve it. For example, in this case, we write and we read from 2 variables. So if we know when we write, we can start the task that is going to consume this data. And as you can see, the total execution time is a bit reduced. We can do it even better. If we know when it's going to read, we can stop the application, the task when it's about to read, wait till the data is written, and then continue. And with this, we can improve the execution time with having this data flow. But it has some problems, and it's usually we don't have enough information to know if what we are doing is good, if it's really worth to run it sequential or concurrently. So for example, these are the same tasks as before, that we have divided them into 2 smaller tasks, depending on when they read and write. But what happens if the workload is too small? Like the cost of creating the thread is much higher than just executing that part of code. Or the time to communicate the data to another node or even inside to another core is going to be more expensive. And, well, I don't know if you know, but if you ever try to measure how much time Linux needs to create a thread, just call this pthread library from Proxys, and it's around 20 or 30,000 CPU cycles when there's nothing else running in the system. So that's a lot of time. So if you want to parallelize create threads that run concurrently and are very small. Just small computations, probably you waste much more time in creating them than just running it. So how do you insert Dataflow into things like C? Basically, automatically, you cannot do it. You have all these scope of variables, arrays, pointers. I don't know how many people here have created arrays, a pointer to an array of pointers to functions. I did that once. So it's horrible. You never know anything, and there's no tool. Everything is going to depend into your data you have. So you cannot make a static analysis of the code. So basically, no compiler will support in doing this kind of things, or the things they do are very basic. So what people do right now is we have some models. There's a family of programming extensions that's called StarSS, and where you, with pragmas, define what are the inputs and outputs of your functions. Like each task, what data is going to need, and what data is going to touch. And then the smart scheduler that, when sees that the dependencies are resolved, will start scheduling the tasks that can start executing. But this is not nice at all. So, I'm going to talk to you now to give you more to think about this, about mathematical programming. And in HPC, we are basically executing mathematical programs. We do physics simulations of molecular dynamics, of structures, of chemistry, and all of these have very nice physical equations behind them. So basically, if you have some programming model where you can just put the mathematics inside, that will be perfect. You don't have to convert any algorithms into C, which is just a set of instructions on how to execute things into a CPU. Yeah, for example, this is a one-dimensional heat dissipation function. So this is like, you can imagine it, because I'm going to explain a bit more. We are going to work with it right now, about a string that is hot and how the heat spreads around it. So for example, if at some point it's very hot in the middle, when you move over time, the heat will start spreading around. So how do you compute this? You make discretization. So here at the end, we have this formula, which is what you execute inside the computer. So this is for each cell. So if we divide our string, for example, in 10 pieces that are the one on the top with the original value, the boundaries that are this one and this one are always with a fixed heat, for example, 0. So we are always calculating the ones in the middle. So you can see very well what are dependencies. And the dependencies in each time step that goes from T0 to T3 in this case are very well defined by here. Like, I need my position. So to know what is going to be my heat in the future, I need my current heat and the heat of my neighbors, which are this one and myself. And that's what we have here. To know my heat, at this point I need the ones of my neighbors. So, yeah, it's what I explained before. So if we are doing mathematics, why don't we just write some kind of mathematical language into the HPC machines? And this is all the problems about communication and optimizations that I was talking before. Why we don't do it like this? So we try to make an algorithm in C or Fortran and put it inside there. But with mathematics, we can do more things. We can reason with them and we can transform the algorithms. And this is something we are trying to do. For example, we can have a formula like this on top, and through a mathematical transformation, we can go to the second one. they are completely equivalent, but if we represent them, we will see now that they are completely different and they have a complete impact on how they can be executed. For example, this is the first one. So if you take this piece is this formula, like the first plus or this one, it doesn't matter, is A. Here we have B, and then we make the multiplication of A and B to get this cell in the next time step. But if we use the second version of the formula, the equivalent formula, we have a complete different graph with the 2 operations only. Before we had 3, now we have only 2, but at some cost. And it's, when we have 3 operations, for example, in this version, these ones can run completely independent from each other. So you can make this group for this thread, this operation, as one in one thread. In the second version, they have this dependency here. So they will have to run sequentially over these. So one thread will be waiting for the other. That's not good. But we will see that we can solve this in some situation. So the transformations allow us to change the computational load while they are still the same result we are going to achieve. So the thing is that when we program, we always think like in natural time. And for mathematical formulas we have there in always like thinking over time. Like I calculate this for this time, then I move to the next time step, then I calculate everything for the next time step. And it doesn't necessarily need to be like that. Because the only limiting factor to calculate every of these nodes is that their dependencies are resolved. So we can iterate kind of in diagonal. Like this is one iteration, this is the other iteration, here with the colors. If the dependencies are dissolved, you can just do it. The problem is, for example, in this case, I don't know if you see it, is that this iteration, you cannot compute it in parallel because there is this data dependency again that you didn't have at the beginning. But if you turn it a bit more, like in this case, you will see that there are no data dependencies anymore. So we could run it in from another, we could change the iteration vector, we could turn it around, and this allows us, for example, to this old formal code we saw before that only uses 2 operations but had this data dependency. And if we turn it around, now there are no data dependencies from this group, between this group, between this group. We have with the previous one, but this was resolved in an iteration before, so all these data are already ready to go into execution. So we have been able to improve the algorithm. Now we have less operations, while at the same time we have been able to maintain the parallelization of it. So I don't know how many people are lost already, but you can watch the video later again. Yeah. So we just, instead of operating over time, as before, which are represented by these lines, we have a new iteration vector called tau now. So what is the impact of the code? So if before we calculate it like this is the C program for this version. It's very clear that this looks very nice because you have these 4 loops like from 0 to 100, from 0 to 5. And now it gets more complex. And that's why it's difficult to reason over it if you want to do it yourself. The advantage is that we can have a complete parallel for that runs all the iterations of it in different threads.
But that last bit of code, that's something you generated, right? You generated by transforming.
Yeah. I mean, I wrote it by hand because the project's still very new.
The
Started
idea is to generate that.
Yeah, the idea is
maintain sanity.
Yeah, exactly.
Thank you.
So now, what's exactly what we want to do in POLCA? So these were the concepts, and now it's exactly what we want to do. So we want to bring all these transformations, all this reasoning over space and time, and extend C with it, so that we can give this information, annotate this information in a C program, and that it can be automatically, the tools can transform it, think about it, and see how it could work better depending on the platform you have. So how do we plan to extend C? And here is where we come with functional languages again. In the approach we are taking right now, we are using Haskell, or a subset of Haskell. So we have a program in C with its algorithm written, with its code, and we just want to say, like, we just write the equivalency of it in Haskell, because we are able to, well, at least one partners were able to make this kind of reasoning of transformations using Haskell, as it doesn't give you the really code that later matches the architecture. We say, don't worry, here you have it. It's already written in C, or it's here written in assembler. So just play with it, rearrange it, and re-execute it as you think is better. We want to address all kinds of architectures that are used in HPC right now, especially CPUs. Well, CPUs continue to be the main part. GPUs in theory too. And especially we want to address FPGAs. Do you know, are people familiar here with FPGAs? Some are, but not. FPGAs are basically hardware where you just define the logic gates inside. And for example, our partner developed one system called Clash. Clash is a subset of Haskell that you can directly compile to VHDL. So you can, and this VHDL is the language you usually use to program FPGAs. So you can directly put your Haskell program into hardware without needing it to execute on a CPU. And that can be very, very impressive sometimes, the gains in performance you have. And it's just directly translated. So we want to address, for example, FPGAs with removing the C code, because you already have it there, written in Haskell. And what we will provide at the end of the project will be, well, the programming model specification, the tool chain, and some reference use cases. So that we are analyzing right now. Lots of partners in the project from different countries and even some companies there. And well, the people who helped me to do the slides, because dealing with all these diagrams can be sometimes tricky. So that's all for my part. Thank you very much.